To evaluate saturated rings, such as the cyclopropane here, we analyze it in both directions around the ring to generate a branched chain. When we return to the atom of the ring that we started from, we record it as a ghost atom. As it lacks further atoms attached, the sequence of atoms for study stops. Let's explore how to prioritize these three substituents. All these substituents have the same nature and order of atoms 1 to 3 bonds from the stereochemistry origin. So for brevity, we will ignore them and consider atoms 4 bonds from the stereochemistry origin. With the 1-ethyl propyl, we have 6 hydrogens. Now, the analysis of the cyclopropyl group, as we have seen, requires that we open the ring, record atoms in either direction, and terminate with a ghost atom of the first atom observed. So, this is what the cyclopropyl group for priority analysis looks like. So we have 2 ghost carbons and 4 hydrogens. On to the 1-propyl-butyl. Here, the atoms 4 bonds from the stereochemistry origin are 2 carbons and 4 hydrogens. Let's keep going. What about atoms 5 bonds from the stereochemistry origin? Well, now, with both the 1-ethyl propyl and the cyclopropyl groups, there are no such atoms. However, with the 1-propyl-butyl group, there are 6 hydrogens, 5 bonds from the stereochemistry origin. The analysis of this allows the assignment of priority. First, if we consider atoms 4 bonds from the stereochemistry origin, we see that while all 3 substituents have 6 atoms, the cyclopropyl and the 1-propyl-butyl have 2 carbons. For the purposes of this stage of the analysis, ghost and real carbons are treated the same, but the analogous atoms with the 1-ethyl propyl group are hydrogens. In atomic number, that is 6 versus 1, so hydrogens give a lower priority, and the 1-ethyl propyl is the lowest 3rd priority. To distinguish between the first and second priorities, we have no difference between the cyclopropyl and the 1-propyl-butyl groups in atoms 4 bonds from the stereochemistry origin. So we go to 5 bonds from the stereochemistry origin. Now here, with the cyclopropyl, there are no atoms, as the prior atom was a ghost atom. But the 1-propyl-butyl group has 6 hydrogens in terms of atomic number, 0 versus 1. Thus, the 1-propyl-butyl is a higher priority, and that's to say, of the 3 groups, the first priority. And the cyclopropyl is the second priority. Much as we saw with the evaluation of the cyclopropyl group, the same methodology is applied to cyclohexyl. Now, how about phenyl? Phenyl is an example of a mancude ring. That's to say, a ring with a maximum number of non-cumulative double bonds, so double bonds that do not share a common carbon. Allenes are an example where 2 double bonds share a common carbon. Now, there are 2 resonance structures of the phenyl group. We know that where there are multiple bonds, for the purposes of priority analysis, we change them to a single bond, and for each bond removed, a ghost atom is added to each atom of the multiple bond. That's the type of the other atom found in the multiple bond. With phenyl, either resonance structure generates the same result when the multiple bonds are removed and ghost atoms added. Now, we aren't finished. We still have the ring to break down to allow priority analysis. We follow the ring in both directions, and when we return to the initial atom studied, we record it a second time as a ghost atom to generate a branched system ready for priority analysis. So here we have introduced ghost atoms for two reasons: addressing multiple bonds and rings. What about more complex mancude rings? Let's take a look at quinoline. It is a heterocycle, so it has at least two different elements. In this ring, there is a carbon and a nitrogen. There are three resonance structures to consider when carrying out a priority analysis upon this substituent. Let's change the multiple bonds and introduce ghost atoms where appropriate, ready for priority analysis. Because the resonance structures have multiple bonds in different places, the resulting ghost atoms are representing different atoms. Many are ghost carbon atoms, but justified from different carbons in the ring, as the color represents, with the outcome being the same, ghost carbon. But in the left and middle resonance structures, the nitrogen ghost atom is on carbon 2, while on the right resonance structure, the ghost nitrogen is on carbon 8A. We can see this more clearly by stripping the detail from the rest of the molecule and focusing upon the differences. The ghost carbons are justified by different carbons in the different resonance structures. For example, the nitrogen in the ring, the left and center resonance structures have a ghost carbon justified by carbon 2, whilst the right resonance structure has a ghost carbon at the ring nitrogen justified by carbon at 8A. Now, a carbon is a carbon for priority analysis. What is important is that I want you to see the resonance structures are different as to how the ghost atoms come about. But again, the consequences for the priority analysis can be seen where different resonance structures have ghost nitrogens at different carbons. Where an atom in all resonance structures has a ghost carbon, it would be evaluated in priority by the atomic number 6. Where an atom in all resonance structures has a ghost nitrogen, not found in this example, it would be evaluated in priority by the atomic number 7. What would happen if some resonance structures have a ghost carbon, atomic number 6, and some resonance structures have a ghost nitrogen, atomic number 7, at the same position? Well, now and only now, it is important to consider the source atom that dictates the various ghost carbons. If we start with carbon 2 position, the left and center resonance structures have a nitrogen ghost atom due to the ring nitrogen, whilst the right resonance structure has a ghost carbon due to carbon 3. So the values of the atomic number influence the priority calculation proportionately to the number of ring atom sources for that atom. Here, there is one ring atom source for the nitrogen atomic number 7 and one ring atom source for the carbon atomic number 6. Thus, two sources, one for each nitrogen and carbon, so the average is 6.5. However, If we consider the ghost atom at carbon 8A, a different story emerges. Now we have again a nitrogen ghost atom with atomic number 7 from one source, but carbon ghost atoms from two sources, one atomic number 6 from carbon 8 and one atomic number 6 from carbon 4A. So we want the average of a 7 and a 6 and a 6. That would be 6.33. Note, not 6.5. Other than these two locations, all other atoms in the quinoline ring have just carbon ghost atoms attached, so the atomic number is 6.00. How about another example? This is quinazoline. The 3 position has been changed from carbon to nitrogen. Everything else is the same as quinoline, but this change does impact our priority analysis. Let's see how. Again, we have 3 resonance structures, and here are the multiple bonds replaced with single bonds and the appropriate ghost atoms added, ready for priority analysis. The colored atoms reflect the position only where there is a variation in ghost atom type between the resonance structures and the source that dictates that ghost atom type. Here is a representation that just focuses on the areas that vary between quinoline and this quinazoline. As we will see, the areas to focus in on are positions 2 and 4. Position 8A is the same for both molecules, and we will not dwell on it here. With the left and center resonance structures, the sources of the ghost atoms found at positions 2 and 4 are the same, namely nitrogen 3 and nitrogen 1. But in the right resonance structure, position 4's ghost atom's source is carbon 4A, whilst position 2's ghost atom's source is nitrogen 3. The position 8A outcome is the same as we discussed with quinoline for the same reason. Now, what does this mean in terms of average atomic number at positions 2 and 4? At position 2, we have 2 sources of nitrogen ghost atom, from nitrogen 1 and nitrogen 3, with the atomic number 7. So the average of 7 and 7 is 7. What about position 4? Now there is one source of nitrogen ghost atom of nitrogen 3 and one source of carbon ghost atom of carbon 4A. So the average of 6 and 7 is 6.5. In summary, here is quinoline with the atomic numbers for its ghost atoms. All are 6.0 except for carbon 8A's 6.3 and 6.5 at position 2. Here is quinazoline, where the atomic numbers for its ghost atoms are all 6.0 except for carbon 8A's 6.3, then 6.5 at position 4, and 7 at position 2.